So now we need to introduce some new ideas to talk about how drag force influences the motion of objects. Because the next thing that we're going to talk about is airflow around objects, which is what influences motions of objects that are spinning as they fly, for example, which turns out to be a very important effect if we want to talk about trajectories in general. So the next idea that we need to introduce is called Bernoulli's principle. It's named after Daniel Bernoulli, part of the very prestigious Bernoulli family, which did all sorts of things in mathematical physics. He lived from 1700 to 1782, so this is not a new idea. But what Daniel Bernoulli wrote down was that if we have steady flow of an incompressible fluid, and let's make the approximation that its height of the flow is not changing, then we can relate two important quantities of the fluid, and their sum turns out to be a constant. And so what Bernoulli's principle says is that 1/2 times the density of the fluid times the velocity of its flow plus the pressure of this fluid is going to be equal to a constant. And the reason why this is important is that if I have fluid flowing around an object, then in order for the fluid to carry the same amount of mass in the flow, it has to either move slower or faster. And so if I have an area where there's high pressure and there can be an area a little bit further away that's at low pressure, then the speed of the fluid will change. And so the pressure, which we haven't really talked about yet, pressure is force per area. So this gets us back to our concept of force again. So pressure causes an acceleration. And so this will change the direction of a trajectory if the pressure around an object is different, say on one side than the other, which is what we're going to see. So Bernoulli's principle applies to, as we said, steady incompressible flow. Now that doesn't necessarily apply to spinning objects in air, but let me just finish explaining the concept here. So let's imagine that we have a pipe or something like that that's going to taper in cross-sectional area. And so I have an opening to the pipe here, and then over here I have an exit to the pipe. And we can connect these two. And so if I have fluid flowing into this pipe at some speed, so this is my initial speed of the fluid flowing in, the same amount of fluid that flows in has to flow out the other end. Since the cross-sectional area gets smaller, the only way I can move the same amount of fluid out as I move in is to move more fluid through a smaller area over time. And so Bernoulli says that the initial pressure over here, since V is smaller, is going to be smaller than the pressure over here. So this is sort of counterintuitive, but the initial pressure where the fluid is moving slowly is much bigger if the speed increases dramatically than the fluid over here. So we have smaller pressure over here, larger speed. Bigger pressure over here, smaller speed. And so this is the Bernoulli's principle. This is part of Bernoulli's equation. And so the point here is just to introduce the fact that motion of a fluid around an object is related to the pressure. In this particular case, for steady incompressible flow, we have this exact relationship. And what we're going to explore in the next couple of slides is something that relates to more realistic flow. One of the things that's missing from this description is that this is only valid for the case where there's no, to use the appropriate term, viscosity. And viscosity is actually what causes air drag. So Bernoulli is valid when there is no viscosity. However, we know that there's air drag, and so there's always viscosity, there's always friction in the air between the object that's moving in the air and the air itself. So we have to go to a more sophisticated treatment that involves using some of the concepts that arise when we have viscosity in play. So this is valid for no viscosity, but it is the first introduction to this idea that pressure and velocity are related. And so now we need to go on to a more sophisticated treatment that introduces viscosity or friction or drag into the motion of the fluid around objects.